on Thursday, February 17th. I have sent you a file, and let me share my screen so you can see what the file looks like. Share my screen. Let's make it bigger. It's an Excel file that basically will help you do any calculations I throw at you with discrete distributions. So this is a problem we did in class one time. This is the baby wakes the mom problem, where it's just we create the distribution. But let's look at this one. This is if you throw one dice and if you throw two dice. So here's a problem. And let's get rid of that. You have the answer, but let's look at standard deviation too. This is a uniform distribution of rolling one dice. Everything is 1/6. So you can roll, if you roll one dice, you get between 1 and 6, and you can have, this is your probability. We don't really need the cumulative density function here, but we can calculate the mean and the standard deviation. One way of doing that, I'll let you calculate both those. Let's make that your quiz assignment in a way. So that's, let's put it here, and let's say you want a box around there. You should calculate this. And maybe we should move everything down a little bit. Well, I'll let you figure out how to do that. I want you to calculate this for me. Boom. Same thing over here. You'll see how to calculate the mean. It's not that hard. You basically have to create one more column, and you can calculate the standard deviation as well. Okay. Then we'll pick some problems in the book to use what we have here to solve some problems. Okay. Now, if you roll two dice, it complicates things. If you roll two dice, here's dice 1, dice 2, and you can get a 1 or 1, and you get a 2. You can get a 6 or 6, and you get a 12. So the maximum, the lowest you can roll is 2, which I think they call snake eyes. And then you can get double 6, which I think in the parlance of craps, they call boxcars. But you see, by rolling two dice, we get different numbers. I get 1 and 1. I can get a 1 and a 2, a 1 and a 3, 1 and a 4. And basically, I've just added those. And the color coding will show that I can get a 2 or a 1. I can get a 3 two ways. So what's the frequency of getting a 1? Or a 2. There's only one way to roll a 2. It's a 1 and a 1. There's only one way to roll a 12, which is a 1 and a 1. There's only one way of getting that. I mean, not 1 and 1, 6 and 6. So if I look at 6 times 6, there's 36 different options here. So the total is 36. And I can send the updated file. Oops. Escape. And then Control B. The total is that. So maybe I'll move this down a little bit. Let's move all this down a little bit. This will leave you room to do totals if you want. But then you just put your answer there. You have other columns if you want to do calculations. And if we look at the mean, which I got rid of in either case, there's a function in Excel, which is quite nice. It says equals sum product. What the sum product function does is takes one array, let's say all the x's, so my value of my dice is 1 through 6. I put a comma. I put the probability of getting each of those, which is actually all the same number. And then what it will do is multiply 1 times 1.166. Let's see if someone's texting me for any reason. No. And add then 2 times 0.1667 plus 3 times 1.667, and we'll do the sum of all that. So you get 3.5. If I do the same thing here, I will get my mean, because it's the probability of the roll 2 times its, the value of 2 dice when I roll it. So here's a 2. I'd want to multiply it by this probability, which is basically the weighted average. It's multiplying 2 times 1 divided by 36, basically. And I think we've covered this, but it's really nice in Excel that it does this for you. So I want to multiply all these, the dice, and you can see that it's a uniform, it's a symmetric distribution around 7. So probably 7 is going to be the average roll. At least that's the mode. And then you get that. So it is 7. Yay. That's why in craps 7 is a popular roll. Snake eyes or boxcars are hard to get. And I'll let you calculate the standard deviation on these. And in fact, I'll let you calculate both on these. It'll give you some product. You have to basically calculate one more column here, which is the x minus x bar by the mean, and taking the square of that. And then you can do the sum product and get the variance. And then the square root of the variance is the standard deviation. So if we want to do it this way, I could say, let's call this, what is the variance? Which we don't talk about a lot, but it is related to the standard deviation. It's the square of the standard deviation. Standard deviation is the square root of the variance. So let's put boxes around that. And then I want you to calculate all this yellow stuff. And I've already given you how to do the mean. It's in the file that you have, but I'll post this file afterwards. I'll call it new or something like that. And you should do this problem. So let's do geez. Variance. We don't do much with the variance except in these sense calculate it and then see what it looks like. So you can see what the PDF of both these look like. Uniform distribution, which is basically a rectangle. Everything happens at the same rate. All right, now I got calculators here, and I've it goes up to, for binomial, it goes up to n equals 20. So if I say, let's say I have 10, and let's say my p is what? So immediately to adjust it, I did some, I've got some, if you look, well, we'll get into that in a second. And let's say I want to just be flipping a coin, 0.5. Well, it gives me the graph of the PDF. It gives me the CDF as well, and it stops at 10. Now, if there's a problem that has more than 20, I don't know that we should be using the binomial distribution. We should probably use a normal approximation, which we haven't covered yet. But it also gives you the mean, the variance, and the standard deviation. So any problem I throw at you that's a binomial problem, you could use this calculator, and we've already had quizzes and stuff where we use the tables to actually get answers. And, oh, what was I going to say? I showed you how I programmed this. It's a little bit complicated because it's, and I know it's hard to see because I can make, let's see, dismiss all reminders, yes. Sorry about that. I was in today's class. I just came in 2 minutes late. Okay, I will mark you here. Stay afterwards and remind me to do that. Well, I can make this bigger. It doesn't make the formula bigger. So what it is, it says if B7, if X, so the X is 0, if it's less than the sample size, then it calculates a binomial distribution. It says comma. So the way the if function works, it gives a relation. You have to make something. If this is true, then it calculates a binomial distribution, comma, and then it gives, if it's false, I just leave a blank space. So I did that for both. I got the same formula in there for, I use the if statement. If, again, B7 is less than C2, which is the sample size, you know, the number of trials of this experiment, number of Bernoulli trials we're doing, then it does a binomial distribution as we've calculated it before. And if it's true, if it's false, it leaves a blank. So it's, you don't get all those funny numbers or, you know, like error statements here. So let's say I want to make it 0.9. Well, it gives a calculation. It gives the mean, the variance, and the standard deviation for that. So you can answer any binomial equation. Let's say the sample size was 15. It changes all the numbers for you, and you can answer almost any question you want to ask. Notice, as the probability goes from, let's make it a full 20 so we can see what this looks like. One thing about the binomial distribution is if you start at 0.005, it gets skewed, pushed up against 0. And then if I make it 0.1, it shifts a little bit. If I make it 0.2, it shifts again. It becomes less skewed right. And 0.3, and 0.4, and at 0.5, where each of the two alternatives are equally likely, the P and the Q are the same, it becomes symmetric around the mean, which is 10. Now, if I look at, let's look at 0.4. I have that distribution, and I have zeros, and let's look at, we've got 20 of these things, so let's see, what should we look at? Let's look at 5. 5 tells us 0.75, 0.75. And kind of remember these numbers. Well, let's copy them over here. Copy. And why don't I just put it right here temporarily? Paste special, which means I don't want to keep the formulas. I want to just keep values and number formatting. So it keeps that. So this is when P is equal to 0.4. Let me move this over just a tad so we can see that. Now let me look at the other symmetric one. If P is 0.4, Q is 0.6. Let's look at 0.6. Obviously the numbers are different, but count these backwards. I have 0, 0. I have 0, 0. I have 0.3. I have 0.3. I have 0.12. I have 0.12. And if you notice, I just basically took the values for 0.4 and flipped them upside down, and those are my new PDFs. Is that clear? If I do the same thing with 0.3 and 0.7, 0.2 and 0.8, 0.1 and 0.9, 0 and 1, or any, if I just flip, if I make what was the Q, the P, I get the same values, but I just flip them over. That's kind of how the binomial distribution works. We didn't have time to really discuss that. So let's leave that alone. We don't really need to remind ourselves of it. We just need to know it. Okay, let's go to the geometric distribution. Remember, this is the one where it's success. It's this Bernoulli trial each time, but it's to the first success. And it can go up. I put it up to 31, but you're going to get oftentimes a lot of zeros. Let's say we go back to the problem of someone shooting free throws, and let's say they're a 70% free throw shooter. We just enter 0.7 in the orange. It calculates your mean, variance, standard deviation. And now I can answer any question. What's the probability that the first free throw I hit, if I'm a 70% free throw shooter, is on the fourth try? Well, it's going to be 1.9% or 0.019. I have 3 decimal places here. Everything else I have 4. I don't know why I've done that. Should we make them all 4? Just to be consistent. We can do that. So at 4, it would be 0.189. What's the probability that on 4 or less, I hit my first basket? Well, it's 99.19. Because it's a 70% free throw shooting. The average time, if I do this over and over and over again, a million times, an infinite number of times, I'm going to get my first basket between the first and the second throw closer to the first. This distribution is always skewed. Let's make it 0.3, which is the complement of that. Oops. Well, it made it bad because I used a slash instead of a point. Remember, undo is your favorite thing. So this distribution always tails off. And now at 0.3, it takes me between 3 and 4, closer to 3 times is going to be my average. My standard deviation is 2.79, which is almost meaningless at this stage of our statistical knowledge base. And I have the CDF. What's the probability that I get it between 10? It takes me between 10 and 5. Well, I can add from 5 to 10. I can look down here in the sum and say that's going to be 21.19% or 0.2119. Or I could say it's going to be equal to the probability of 10 or less minus not the probability of 5 or less, 4 or less, and I get 2119. I can answer every question. What's the probability that it takes me more than 3 times to get more than 3 times? Well, this is less than or equal to 3 times. So if I say equals 1 minus less than or equal to 3 times, the complement, well, all I did was get 1 here. That was brilliant. I didn't put the minus. 3 or less is more than 3. It's going to take me 34. The probability of that happening is 0.343 or 34.3%. All right, let's go to hypergeometric. This was, let me make it bigger so you can see it. I only have it up to 30. I don't think, hopefully we won't have problems that are more than this. But let's make it bigger so you can see it. This is the card problem, right? What's the sample size? I'm going to get a card of a hand dealt to me randomly without replacement of 5 cards. Let's say I want to know what's the probability of getting a flush, which is all, we did this last time, which is all the same suit. So let's say it's hearts, diamonds, clubs, or spades. And let's say we were interested in hearts. I want to get a flush. All 5 cards are going to be a flush. Now this one we have to 4 decimal places. We have the hypergeometric distribution. I have the same iffy thing here. That's a little bit more complicated because it's a min between this and this number. So in this case, it's going to be 5. So it stops at 5 because that's how many cards I'm picking. So my sample size is how many I'm taking. The number of successes in the population is 13. The population size is 52. So it's a probability that I get 0, 1, 2, 3, 4, or 5 hearts. Now I have PDF and CDF again, and it does that. Now let's say, what's the probability of getting a flush? 0.0005, 0.05%. Now, if I want to say, what's the probability of getting a flush, and I don't care what the suit is, well, the number of suits are 4. So I'm going to multiply the probability of each suit. They're independent. The suits are different. So I'm going to get now the probability of like 0.2% chance of getting a flush dealt to me. Notice that we're not playing any game, and sometimes in poker you can turn in up to 4 cards and I give you 4 more cards. We're not allowing that to happen. We're not looking at a game where you have 5 people and 1 deck of cards so that the probabilities involve all these other 5 people getting cards and you wondering what they have and not have and all that, because that really changes the probabilities too. We're just taking it, shuffle a deck of cards, give you 5 cards. What's the probability that you were dealt 4 hearts? Now, the harder thing in a row to do now is if you were going to ask the question, what if I got a pair of cards. Well, we're still getting 5 cards, but now we're looking at the probability. I want a pair, 1 pair. And 1 pair, that means is 4 2s. Let's say getting a pair of 2s. So let's do the calculations there. So what's the probability of getting exactly 2 2s? 0.0399. How many different? Now, this is complicated because if I want to say what's the probability of getting 1 pair of anything, I don't multiply that by 13 because there's going to be some conflict. If I have 2 2s, I could also have 2 jacks. But if I'm only getting 2 2s, you see how this hypergeometric does not answer all the questions you might want to ask about card playing. Dealing cards and poker hands are like ridiculously hard probability. So what you probably want to do is just go to Wikipedia to answer those. But if you have, let's say, I don't know, we'll do some problems and we'll come back to this. The Poisson distribution gives you a mean. And so let's see, here is the output of this. You would put in the orange parts. You put in a mean. And we don't know how big the mean is, so we don't know what the x's are going to be. I mean, if I make the mean 5,000, well, all these are going to be 0 and 1 because 5 and 11 are so far away from 5,000 that the probability of getting 5 or something happening at 5 or 11, if the mean is 5,000, is never going to happen. So it's kind of got to be close to that. And I didn't calculate the mean or standard deviation for hypergeometric or Poisson. I'll do that after class when I send the file out. So you have that if you are so interested. But the mean of the Poisson is just the mean, period. That's what it is. And I don't care about the standard deviation too much. So it's not important. But let's say, how does the Poisson distribution work? Let's do something in class that we tried. Geometric, hypergeometric, Poisson. So if we look at the average number of fish caught in an hour is 8. Of interest is the number of fish caught in 15 minutes. So if we have 8 fish, average, well, let me bring the textbook up. It's just easier to do it that way. You can see it better. Let me bring this up. Let me bring OpenStack statistics. Let me sign in. View it online, which is really makes it kind of convenient. Let's go to discrete random variables, and let's look at Poisson. Yeah, I know. Thank you for reminding me that every time. The average number of fish caught in an hour is 8. Of interest is the number of fish caught in 15 minutes. The time interval of interest is 15 minutes, so 8 divided by 4 is 2. That's going to be my new mean, 2. And then we can ask any questions. They ask a question. What is the average number of fish caught in 15 minutes? We did that. Let's say now I want to find out the probability that we caught 1 fish or we caught 3 fish. And I put 2 numbers in there. It can give me the difference between the CDFs. It gives me the PDFs for both. So the probability of catching 1 fish is 0.2707, 27%. The probability of catching 3 fish in 15 minutes is 18. The probability of catching something other than 1 fish is 1. Well, here's the CDF. 1 or 0 is 0.4. More than 1 fish would be 1 minus the CDF, which is 0.59. If I want the difference between 3 and 1, which would mean 3 or 2, it's 45.11. That's how you read this. All right, so I can put in a couple other numbers. If you want to expand this and put in more numbers, be my guest. Let's look at another problem here. The bank expects to receive 6 bad checks a day on average. What is the probability the bank gets fewer than 5 bad checks on a given day? Well, they didn't say we catch 8 fish an hour. Now we're interested in how many fish we catch in 15 minutes. 6 bad checks a day, and they're asking questions about a day. So we get the item of interest is number of bad checks. They get 6 bad checks a day. And what were the questions they asked here? Of interest is the number of checks the bank receives in 1 day. So the interest level is 1 day. Let X be the number of bad checks. Okay, so that's a probability question. Let's say what fewer than 5. So if I just I can leave 1 in there, but let's put 5 here. 5 would be an interest. The probability of receiving exactly 5 checks is 16.06%. The probability of the CDF of receiving less than or equal to 5 checks in a day is 44.57%. More than 5 bad checks in a day, and what are we at? 55.43. 1 minus the CDF. The complement of less than or equal to 5 is more than 5. So you can answer these kinds of questions easily using this little Poisson calculator. If you really want to learn this, make up your own binomial, geometric, hypergeometric, and Poisson calculator in Excel. I would imagine it would take you a couple, 2-3 hours to do it. I'm just guessing, but you would really get to know how to do these kinds of problems, and then you could use your own calculator to do it. Let's see if our answer is right. we have 44 point. This is the number we're looking at right there. If I was going to answer this question, I would say, ooh, there's my answer right there. What's the solution? Well, they just have probability less than 5. They didn't actually do it. All right, so here, let's look at this one. You notice that a news reporter says, on an average of 2 times per broadcast. What is the probability that the news reporter says, like, you know, hey, there's a news story today about a man that robbed a bank. So I guess uhs are bad. If you've taken business communications or public speaking, they really count the number of uhs or does or that you say. I've seen politicians use Senator Ted Kennedy was brilliant at it. When he was trying to collect his thoughts, he would just say, Chairman of the Senate, I would like to raise a proposal about, and then he would always use up. When people were allowed to smoke on the Senate floor or in meetings, people would take, instead of saying they would take a puff on their cigarette or take a puff on their pipe instead of saying so very interesting. Anyways, it's 2 times per broadcast. What is the probability that the news reporter says more than 2 times per broadcast? This is a Poisson problem, as you're interested in knowing the number of times the reporter is saying during a broadcast. What is the interval of interest? What is the average number of times? Well, here, let's just go to our calculator. Now we put in 2. And let's say, we can put 1 and we can put 2. And okay, so now I have everything I need to answer a question about 2. And it says, what is the probability that more than 2 times? Well, the CDF is 2 times or less. 1 minus the CDF is 0.3233. So that's the probability of interest at this point of the question. So 3233, 32.33%. Are we correct? Well, they just write it. They haven't actually done the problems. We should do when we do the problems. This is Leia's answering machine. Do we care about Leia's answering machine? Let's look at this. According to Baden, an email management company, you get, well, we did this in class. Let's look at this. According to a recent poll by Pew Internet Project, girls between the ages of 14 and 17 send an average of 186 text messages per day. Whoa, let X be the number of text messages. So I don't have to adjust this. This is per day. We're still looking at per day. The discrete random variable takes on the values 0, 1, 2, whatever. The random variable has a Poisson distribution with the mean of 187. So I can just put 187 right in here. And guess what? Do I expect 1 or 2 text messages to have any probability? It should probably be 0s and 1. Now let me get rid of this because we're not looking at it. Let's go back to the problem statement. What is the probability that the girl sends exactly 175 text messages? Okay, so let's put in, and then what was the other one? The other question was 150. Okay, so let's put in 150, and then let's put in 175. The probability that someone sends exactly 175 text messages is 0.02. Less than or equal to 175 is 20. More than 175 is 79.88%, almost 80%. The probability of sending exactly 150 is 0.006, 0006, or 0.06%. The CDF of that, less than or equal to 150 text messages, is 0.3%. More than 150, so 151 or higher, is 99.7. In between 150, well, it's not in between 150 and 175. It would be in between 149 and 175 would be 19.82%. What are the exact questions? So what's the probability? Exactly, at most, is the same as 150 or less. So the answer to part A is this. The answer to part B is this. So you can calculate everything you want. What did they ask the question? What is the standard deviation? I don't know. What is the mean and standard deviation of the Poisson distribution? The standard deviation is square root of mu, so we can do this. So let's add some lines in here. Insert. Insert. So we have variance. I think we did this last time. I just don't remember what it was off the top of my head. Standard deviation. And let's make. All right, and let me make these yellow because these are going to be calculations. The variance is equal to the mean. The standard deviation is just the square root of the mean. Do I need all those decimal places? No, let's take it maybe down to 2. So standard deviation is 13.63. Again, standard deviation is a hard thing to look at. It's not as easy to interpret as range. All right, so we did some of those problems. Let's look at some problems in the hypergeometric one. They don't give very many problems here because it's a specific one. So let's see, this is example 4.25. Why don't we look at that? So let's go to our book. And let's go to the hypergeometric and see what we got here. What's a probability statement? Well, we did this one with the vowels. Let's see. Okay, suppose a shipment of 100, did we do this too? 100 DVD players is known to have 10 defective players. An inspector chooses a random sample of 12 for inspection. He is interested in determining the probability that among the 12 players, at most 2 are defective. The two groups are 90 non-defective and 10 defective. The group of interest, the first group, is the defective group. Notice they use group of interest. They don't use success anymore because the probability question asks for probability that most 2 defective. The sample size is 12 DVD players. There may be non-defective or defective. So we're going to look at these DVD players. Let's bring this over here. And we can look at it side to side. I don't know why I haven't been doing that. Probably I'm not good at this. Okay, so here we go. What's the sample size? We're going to collect 12 DVD players, right? Okay. What's the number of successes in the population? Well, here, items of interest. So 10 defective players in it. So if I put 10, as soon as I hit enter, it's going to increase to probably 10 or 12. it goes to 10. It's going to take the minimum of these two. Can't get any more than 10 out of a population. Now, what's my total population? It was 100 DVD players. So there's my population. What is the question? That they asked. He is interested in determining the probability that amongst the 12 players, at most 2 are defective. At most says CDF, 2 or less. I'm going to get 90.19%. Let's see if we did that right. Well, there's a problem statement. They didn't give us the answer. Let's do one where they have the answer. Let's do this 4.24. You're president of an on-campus special events organization. You need a committee of 7 students to plan a special birthday party for the president of the college. Your organization consists, we did this one already too. Well, we'll do it again. You need a committee of 7 students to plan a special birthday party for the president. Your organization consists of 18 women and 15 men. You're interested in the number of men on your committee. If the members of the committee are randomly selected, what is the probability that your committee has more than 4 men? Okay. Are you choosing with or without replacement? Well, if you're choosing a committee, it's without replacement, which makes it kind of, and you have 2 groups, makes it hypergeometric. So what's the sample size? How big is the committee going to be? A committee, and this, notice this is professorial stuff. You need a committee of 7. They've written it as a word. Why do they do that? And then all the other things are written as numbers. To confuse you. That's why professors do that. I either write them all in number. If I am mindful of it, I try to write them all in numbers, not confuse you with the 7. But we're choosing a committee of 7. So we're at 7. And what are the number of successes in the population? Well, there's 15 men in the population. We're interested in the number of men on the committee. And then how many are there total? How many are there total? 18 plus 15. Well, if you can't add it, you could go here and just say equals 18 plus 15, or if you just add it, it should be like 33. And there you go. That gives you all the probabilities. You notice every time I entered one of these numbers, it changed. So now what's the question? I can answer any question that you throw to me, a probability question, because I have all the numbers. But they're asking on the committee, what is the probability that it has more than 4 men? Well, here's less than 4 men, right? Less than 4 men. If I wanted to, I could add a column for 1 minus CDF, and then I could really not have to do any calculations at all. And it's going to be equal to 1 minus this. Oops, and because I didn't put the thing, it gives me all these values, but here's 4. The complement of 4 is 13.1%. 13.01%. Okay, they did it, but they didn't give us the answer. Wasn't that nice? What's the problem with just setting it up and not getting the answer? I would rather have you get the entire, give you the ability to answer any question. All right, let's go back here and look at the geometric distribution. Okay, an instructor feels that 15% of the students get below a C on their final exam. She decides to look at final exams selected randomly and replaced in a pile after reading until she finds one that shows a grade below C. We know the probability that the instructor will have to examine at least 10 exams until she finds one with a grade below C. What is the probability question stated mathematically? But also, what is the probability that she has to look at least 10 exams before she finds the first one that's graded below C. Well, geometric distribution. It only has one parameter in it, and that's the probability of the Bernoulli trial. You select one. We know that 15% of the students get below C, so let's do 0.15. Boom. That changes all the probabilities. It gives me my mean, my variance, my standard deviation. I should, probably I'm going to have to look at an average of between 6 and 7. 2/3 is the weight of 7 to find the first one. But she wanted to know what's the probability that I had to look at 10 or more. What's the complement of 10 or more? 9 or less. 9 or less is here. 0.7681. So 10 or more, if I just move this over a little bit, and I do, if I say this is equal to 1 minus this, I get 23.16. Do you think you could do some problems like this in Excel using my little calculator? Why not? All right, so let's look at this. This is a problem with the defects, right? We're choosing a sample size of 7, and we're finding the probability of, oh, this was the men and women. We didn't do that. Let's go back to that. Let's go back to hypergeometric, and let's enter that one. And let's also look at it as a binomial distribution. Oh, Professor, why are you doing that? Why are you making us look at two distributions that are like the same thing? You're confusing the living daylights out of me. All right, so here's the shipment. You have 100 DVD players. So the total population is 100. Boom. An inspector chooses 12 for inspection. So the sample size is going to be 12. You determine finding amounts of 12 that there are most 2 defective. So out of 100, 10 of them are what? Defective. And what was the question here? They want to find the probability that 2 or less were defective in a sample of 10. 90.19%. This also sounds like a binomial problem, right? Because we're choosing 10 randomly. The probability of anything being a defective is 10 over 100, or 0.1. We should get the same probability for the CDF of the binomial distribution as a hypergeometric distribution. Let's test that theory out. We're choosing a sample of how many again? First thing to go is 12. First thing to go is short-term memory. So we're choosing 12, and we're choosing a sample size of 0.1. What's the probability of 2 or less? Why do we get a different number? Why do we get a different number? We get 0.889. What do we get in a hypergeometric? We got 0.9019. Can we say it's rounding error? I don't think we can. I would use a binomial distribution for this, but that's okay. There are only 10 defective. Write the probability statement. Probability is x is less than 2. Maybe the hypergeometric is wrong? I think I did it right. It's pretty close. 90.19. The binomial says what? Well, we're assuming an infinite population too here, which might make the difference. This is the problem with statistics. You get something slightly different. Remember, these are models. These are not accurate to 1,000% or 100%. I think the problem here is the fact that there's no sample. We don't know what the population. We're assuming an infinite population here. The binomial distribution assumes an infinite population, where the hypergeometric assumes a finite population of 100. And there's 10 out of 100 that we're looking for. So it's slightly higher probability finding 2 or less than the binomial distribution. But what's the difference between 88.9% and 90.19? Well, ask any student, they'll tell you 90.19 is an A minus and 88.9 is a B plus. So there is a difference. But now you see how to do every problem in the book. Should we pick some problems to do for your homework? I haven't done that yet, but let's do it. Let's look at homework. That you can do. Well, here they're giving you all the problems by type of distribution. That's no fun. Don't you want to figure out what the problems are? The odd numbers ones have the problems, the solutions are available. So let's look at, well, I guess we'll pick one of each. You already know what kind of distribution it is. That's not no fair. It's probably better to have the general problem. Let's do one of each. A customer looking to buy a red Miata will call a dealership until she finds a dealership that carries a car. Okay, so you're already going to know what kind of distribution it is. Let's do the first one of each of these. Let's see. Oh, 1,000 babies. I would use the normal approximation. Okay, the school newspaper reporter decides to randomly survey 12 students to see if they will attend the festivities this year. Based on past years, she knows 18% of the students will attend the test festivities. Let's do problem 88 for your homework. That will be your binomial problem. Chapter 4, number 88. So you can make a copy of this and do the binomial problem on the binomial tab and format it so that I can see the answers, not like I formatted them. And maybe I'll do one so I can show you can see what I think formatting should look like. All right, this lady is looking to buy a red Miata. We'll call dealerships until she finds one. She estimates the probability of an independent dealer will have the car will be 28%. We are interested in the number of dealers she must call. Well, first of all, this is not a real problem. Why? Because you would go to a dealership and ask them to find you a red car, and they would find it for you and have it shipped to them. But okay, let's do this. Find the probability she must call at most 4 dealerships. Find the probability she must call 3 or 4. So let's say chapter 4, this is our first one was our binomial, the second one was our geometric. So let's do 104. This is your quiz. I'm going to count double because it's homework. Can you work together? No more than 2. I don't want to see 3 people turning in the exact same thing. I can't keep you from working together in groups of 3, but boy, it better look different to me. And let's go with North Park honesty. If you turn it in with 2, put both names on the file when you turn it in, or when you turn it in, let me know that you worked with someone else and who it was. Okay, hypergeometric. Group of martial arts students is planning on participating in an upcoming demonstration. 6 are students of Taekwondo. 7 are students of Shotokan, karate. Suppose that 8 students are randomly picked to be in the first demonstration. We are interested in the number of Shotokan karate students that are in there. In words, define the random variable, list the values that it may take on. give the distribution, which you have to look in the book to find out how the book expresses the distribution. It may be different than how Excel does it. How many Shotokan karate students do we expect to find? So that is the mean. And we haven't done the mean. I like that. That'll allow you to do something. And I want to see the full distribution on your sheet that you turn in for all of these, because I'm giving you the calculator. So let's do 112. Let's do 112. Or maybe 114 is better. Find a probability. Oh, yeah, let's do 114. That's better. 114. 114. Suppose that a technology task force is being formed to study technology awareness amongst the instructors. Suppose that 10 people will be randomly chosen to be on a committee and form a group of 28 volunteers. 20 who are technically proficient, 8 who are not. We are interested in a number on the committee who are not technically proficient. So we'll do 114. Do you realize that when North Park first went on COVID and everybody had to use Canvas all of a sudden, the number of professors, there was like 20% of the professors that weren't using Canvas. I don't know how they managed their course without using Canvas. The grade book and all that. It's crazy. Okay, Poisson. Aaron, I guess this is for you. It's the hospital in Manila. The Dr. Jose Fabella Memorial Hospital in Manila in the Philippines is one of the busiest in the world, with an average of 60 births per day. Let X be the number of births in an hour. Ooh, are we dividing 60 by 24? I think babies, how would you interpret that? Someone tell me.
Maybe we divide 60 by 24 and then round it down.
Or use it as a, yeah, I think you'd have to round it down probably, or round it up, either way. Do babies, let's say the hospital's only open, could the hospital only be open for 12 hours for births? Let's say I'm a new hospital administrator and I say, listen, the maternity ward, let's only keep it open 2 shifts. I don't want to work 3 shifts. Do babies follow that rule? Babies come anytime they want, don't they? So it's got to be 24 hours. Sketch a graph of the probability distribution. Oh, I have to put the probability distribution graph in there for that. Well, maybe we'll let you do that. This is a good one. What's the probability that the maternity ward will deliver 3 babies in 1 hour? What is the probability that the maternity ward will deliver at most 3 babies? Yeah, this is a good problem. 118. All right, who's already got them done? Anybody? I know that's a bad question. Who would like to see a similar problem done to any of these? This is your time to ask me questions. You think you can do this by Tuesday? See, this is a problem with online. It's a flat line. You can't walk in front of your desk and ask you a question. Do you want me to do more problems? Want me to do one? We'll pick one randomly from binomial, geometric, hypergeometric, or Poisson, and I'll answer the question exactly like I want to see it answered?
Yeah, you do one more like that.
Let's do it. Someone replied to the conversation. Yes, well, Both Anthony and Bianca said yes. I think I will do it. Does anybody have a preference if I do a binomial or a hypergeometric or whatever? It doesn't really matter because the way we've constructed it is you can look at the table, right? Let's do, I don't know. Let's go back to the book. I'll share my screen again. And let's bring this up. Poisson, hypergeometric. I like geometric. I don't know why I like geometric problems. What we're doing 104. Let's look at 106. It has been established that only 30% of California residents have adequate earthquake supplies. Suppose we are interested in a number of California residents we must survey until we find a resident who does not have adequate earthquake supplies. In words, define the random variable. Okay, so let's put this over here. Let me create another one, another sheet here. And let me call this number, I don't know what I call it, 106. Okay, so we decided this is what kind of geometric distribution. So let me go here and copy my geometric, copy. Sorry. Paste. I think this is going to show me, it's going to take me back to the other picture. So I got to probably make a new graph if I want to do that. I would just make a new file of the one I send you, your homework file. So let's put this here. What do we say? The first thing they said is 30%. So we're doing a geometric with 0.3. There we go. I got it. Do I want to look at a picture? I want to get rid of all these extra stuff that don't mean anything. And let's insert a graph. I have to highlight what I want it to graph, or it's not going to graph anything. Let's graph it to, I don't have to graph it all the way to 30. Let's graph it to 22. Insert recommended chart. Let's look at that. Beautiful. Isn't that nice? And if I click on the bars, I want to click on all the bars. And I want to reduce the gap. And I want to have a solid line border. I want it to be white, and I'll make it pronounced. There we go. So now I know what it looks like. What are the questions?
Professor, I think someone is calling you.
Oh, who's calling me? Oh, they want to be let back and will it be recording of the Zoom? Yes, there will be. I didn't hear. I would have heard the call. Maybe someone was calling someone else. Maybe someone was calling you. Let me see if there's anything in Teams. Someone's calling me. Activity. Chat. All right. No, no one called me on Teams. But thank you. Let's go back here. Let me copy this. and take it to Excel. There's my Excel. And I'm going to enter insert a text box. What's a text box? It's a box.
You're muted. We can't hear you, or at least I can't.
Yeah, for some reason you said I had a phone call, so I went and muted myself instead of doing anything else. Sorry about that. All right, so what I did was I copied all the questions and I put them in a text box. And I can make the text box bigger. I don't need that anymore. So let's make the text box bigger. And I can make the questions if I want bold. And a sample of how many sample, we don't have the, there was no sample in this question, was there? Oh, the first, number of California residents we must survey to find the first one that is not, that does not have adequate earthquake supplies. Okay, that's good. List the values that X can take on. I would do it this way. This is open-ended, right? The geometric distribution is open-ended. So I'll make that bold. And I'll say X is an element of, I would say, the natural numbers. What does that mean? Which is equal to the set 1, 2, 3, 4, ... Close set. Okay. That's easy. C. Why do you have to do all this? I don't know. Why not? X has the distribution, which is the tilde of geometric, and there's only one argument in there, and it's the mean, which is 0.3. So that answers that. What is the probability that we must survey just 1 or 2 residents until we find a California resident that does not have adequate earthquake supplies? So we want the probability of 1 plus the probability of 2. Which is also equal to, and I'm doing this like, you could do it both ways. You could do 1 and 2, which would be these two numbers added together, which if you see down here is 0.51. Or you could just do the PDF, the CDF of probability of X being less than or equal to, let's put it less than, and I'll underline that. Command underline 2. So that's the CDF Oh, it's underlining everything, sorry. Let me make everything else not underlined. So that's going to equal that number. So if I want to put this number here, if you want to show me that I know where you got it, rather than you just made it up, I don't mean to make that yellow, I mean to highlight it as yellow. Equals 0.5100, which is also equal to 51%. Okay, so what was this? This was number D. Make that bold. And we have E. What is the probability that we have to survey at least 3 until we find at least 3? Well, in this case, what do we want? That has to be 1 minus the probability that x is less than or equal to 2, right? Which equals 1 minus 0.51, which equals 0.49, which also equals 49. You don't have to, you can either give me percentage or thing, whichever you prefer. I'm putting both. Make that bold. Let's make it bigger. Let me do this. Okay. How many California residents do you expect to survey until you find a California resident who does not have? Well, this is the mean. Mean, which also is equal to expected value. You could use both terms. What's the mean of this distribution? 3.33. And the way, can you really have a decimal place as a person? No, it says you have to do between 3 and 4, closer to 3 is what that means. F, but I round to have the exact number. Bold. How many California residents do you expect to survey until you find a California resident who does not have? Is that the same question? Who does have adequate earthquake supplies? California residents do you need to survey until you find a California resident who does have? They flipped the question, haven't they? Well, how do we get this mean? We take 0.3 and divide it by 1. Isn't that what we do? So let's say we went here and said, what's the probability of people that have, let's say we change this to 0.7, excuse me. We'll just leave that as it is. But if I change this to 0.7, now I'm doing, if I change this to 0.7, now my mean changes to 1.43. Mean is equal to 1 divided by 1 minus 0.3, which is equal to 1 divided by 0.7, and the calculation is 1.43. If you wanted, you could just make a new table here. Make it bold. Make this G. Okay. Does that look pretty? You can, if you want to, put borders around it or shade it with, you know, a different color to make it look nice. And then you could put answers. You want to make that bigger, you could do that. Just pretty it up so it looks like you're turning it into your boss's boss. Pretend I'm your boss's boss. Now I can see what you did. And then I'd probably go back and say, change that to 0.3. Or I could copy the whole thing over and put her, you know, create 2 more columns, insert 2 columns here, and then write the 0.71, but this is adequate. So you see, my philosophy here is to draw the probability table, write all the probabilities, so you're not just entering all this Poisson or geometric stuff for one probability. Does that give you an idea of how I'd like to see these done? I will send you this file. I would make a copy of the file. Well, you can use the same file once you, I mean, the copy is going to be, the actual file is going to be in both the announcement and the homework assignment. So if you download it, you can just redo it, save it with your name on it, or if you're doing it with 2, let me guess that I might get Lind and Martini working together. I'm just taking a wild guess there. So it would be, you know, homework, whatever it is, and then you turn it in on Canvas as an Excel file. I wanted you to find the mean, variance, and standard deviation for this problem, and the 4 problems that we talked about, number 88, 104, 114, and 118. And I did 106 in detail for you. All right. More questions? Do you want to see another one, or your brain's full? I'll take that your brains are full. I will stay on till the last person gets off. I'll stop the recording in case anyone wants to talk to me.